Hi guys, welcome back to my channel Programming with Pirai. In this video, we are going to see about Leetcode question number 700. Search in a binary search tree. You are given the root of a binary search tree and the integer value back. Find a node in the binary search tree that the node's value equal to the val and return the subtree rooted with the node. Such a node does not exist, then return null. So we want to find whether the given value is present in this binary search tree or not. If it is present, then we want to return that root value, not that value. We want to return what? The root value. Okay. And if it doesn't present, we want to return what? A null. Okay. We can see, let's take this as our tree. Okay. In this example, see here, let us take search element as maybe 1. Then you want to return this 1. Okay, if the search element is 2, I want to find whether 2 is there. Yes, 2 is present here. So I want to return what? 2, 1, and 3. So I want to return this node alone, this particular node alone. Can you understand this? Okay, if the search element is something like 5, then whether 5 exists, no. Then I want to return what? A null. Hope you understand this. Now, how to do this? Okay, first of all, the first method is that just traverse the entire tree. Just traverse the entire tree by using any order traversal. By using order traversal or VFS traversal, anything. Okay, use pre-order, post-order, and in order, anything. You can do anything and find the answer. So such that the time constant will be what? O of n, because we are just iterating towards each and every node. And also space quantity is what? If I use a VFS traversal, it is O of h, right? Because we are using what? A rector set stack. So it will be O of h. So this is the normal fast technique of searching a node in a binary tree. But it is what? It is a binary search tree. Okay. What is the special characteristics of this binary search tree? I can say the left child is always what? Is less than the root. Okay. What is the property of right child? Right child will be always a greater than the root. So this is the property, right? So this property leads to what? Leads to a deletion of entire child or subtree. Yes, see here, if something like this one, and there are some subtree like this. Take for example this 3. Now here are some subtrees. Now I can say if it is started with 1, okay, and it is started with 5 something. Okay, if I say the current search value is greater than 3, then where should I go? Should I go to the minimum? No, I can ignore this whole subtree, right? Because this whole subtree will have what? This whole left subtree have elements which are less than this 3, right? And then this whole right subtree have what? The elements which are greater than 3. So I want to go to this whole subtree, right? It is like what? It is like a binary search. It is like a binary search in non-linear data structure. Okay, so this is the basics of this binary search tree. So how we are going to do this? Okay, initially I will base here. Let us take the search element as what? Search element as 2. Okay, now I'm going to check whether this 2 is less than or equal to or greater than this 4. So I can say it is less than 4. So I will go to what? A left side. Okay, I'm going to here. Now I'm checking whether it is equal to or greater than or less than 4. So it is what? It is equal to 2, right? So search element is 2. So I want to check whether it is equal to greater than or less than 2. So it is like equal to 2. So I can say this is my answer and I will return this root value. And from this 4, again I will return this root value. So I will get what? The root value as 2. So 2 will be my output. Yes. Now if the search value is something like 5, then what it will return? Okay, let us take the same example. Now the search element is what? Search element is 5. Okay, now initially I am here. Okay, so 5 is greater than or equal to or less than 4. 5 is greater than 4. So I want to move to what? A right side. Don't move left side. It is in right side, right? So that we are ignoring what? We are ignoring whole left subtree. Okay. Now again, I am checking this 7. Whether 7 is less than or greater than or equal to 5. It is greater than 5, right? So I want to go where? I want to go to the left subtree, ignoring the right subtree, right? Okay, it is null. Then I want to return what? Then I want to return and null to it. Again, this 7 will return what? And null to it. So such that I can say for 5, it is what? And null. Can you understand this? So this is how our code looks like. Sorry, this is how logic looks like. And again, what is the time constant specifically for the solution? I can say my time constant will be again n. Okay, in the worst case. And at the best case, it will be O of H. I will explain you why best or average case. And this time it will be O of H. And also the space constant will be O of H because we are using what? A DFS traversal here. So because of this DFS traversal, we will create an internal recursion stack. And that leads to what? That leads to O of H, which is what? The height of the stack. This represented as what? H. Hope you understand this. Now, let us see why I am taking this as what? O of n and O of H as average case. Okay, let's consider tree like 1, 2, 3, 4. Now, if I ask you to search of 4, okay, then initially you are at where? You are at here. Now you will be going here, then going here, then going here. Now again you will return, and return. So how many times you have traversed? We have traversed 4 times. And number of nodes is 4. That's why our time constant will be what? O of n. So this is the worst case. Okay, in Western average case, let us take an example like this. Okay, that given 3 such result, best case. Okay, in this, see here, we ignore the entire left subtree, right? We ignore the entire left subtree. It is like we are going to one path. So it is like from root to we are going up to what? Up to the leaf path, which means it is gives what? O of H as our time complexity. So in binary search also we are getting what? A log n, right? Log n. Here also, this log n is equal to this O of H only. Because the height of the tree will be lies between what? Log n times, right? Log n times the tree. The tree node is n, number of nodes is n. Then it will be what? H will be log n times only for a complete binary tree, right? So in best and average case, the given tree will be what? A complete binary tree, or the levels will be same. The levels will be greater than or equal to or less than 1 like that. So the absolute difference will be greater than or equal to 1. Sorry, less than or equal to 1. At that time, we can use what? We can use what? O of H as our time complexity. So this is the important thing you have to note. Don't say that it is always O of H. In some cases, it falls to what? O of n also. In a skew tree. Yes, observe skew tree. In skew tree, it will be like this. What is my skew tree? It's like this. It will be like a slanting person like this or like this. Okay? It is in our same path. So in this case, it will be traveled up to what? O of n times. Okay. Now let us see the code. See here. First of all, I'm just returning what? Tree of root. Okay. Now in this root, in this tree function, what we are doing? If not root, then what should I return? Just none. Because in the drawing of an also, I written what? And null, right? Why? Because they are asking if it is not found. That means what? We have reached the null, then we will return the null. That's it. Okay, if not root dot value, if the root dot value is equal to the val, then what should I do? I just return the root. Simple. Okay, if root's value is less than val, then what should I do? I just return what? Tree of root dot right. Just this tree of root dot right is returned, right? I'm going to then right subtree and returning it. That's it. Okay, else what should I do? I just going to the left subtree and returning it. Simple, right? So this is my BSP searching approach. Okay, in binary tree searching approach, we will use what? We will either use a level order, pre-order, post-order, anything, any traversal, and you just apply this same algo, but this if else are not there, right? It is like a linear search. Searching in a in a binary tree is like a linear search, and searching in a binary search tree is like a binary search. Okay, now this is submitted. Thank you.
Yeah, I'm a dog nom.
Just a little bit. I feel really happy.